So what do you get in the box when you buy the speed of sound system? Well, you get the main control unit, which has got a microphone in here. It also comes with a battery, which I've put in the side. You also get the slave unit, which has got another microphone in here, and you get this big long cable to connect them both together. What doesn't come in the box but you are going to need is a timer. Now the system works with both of the Lascelles timers, but I'm going to show you how to use it with this one because it's a little bit cheaper. If you wanted to use another manufacturer's timer, there is advice on how to do that in the instructions. So why use the Lascelles system over something else? Well, the way that the experiment suggested to do over here in the UK is that you'd get two microphones, attach them both to an oscilloscope, and then make a noise, and then you look at the time delay between those two microphones receiving that same signal. Now, obviously, to do it in that method, you have to use an oscilloscope, and that presents a bit of a barrier for some people performing that experiment, just because they don't know how to use that piece of apparatus. You also have to make sure that the microphones that you're using are amplified enough so that the signal can actually show up on an oscilloscope. So what our equipment lets you do is just make sure that you can still access that experiment, but just without using any complicated equipment. You can still use an oscilloscope if you wanted to, so there's terminals on here to do that, but like I say, it's not a necessity. So how does the experiment work? Well, it's very similar to what I've just told you. You have two microphones separated over a known distance, and then you make a noise near this one and look at the time delay. And then simply just use speed equals distance over time, and then you can calculate a value for the speed of sound. Now you can just do it off the one reading, but we're physicists and we like to make graphs, so let's do that. So this is how the equipment is set up on the floor. I've got the control unit on the right hand side with the timer and the slave unit on the left hand side, and they are separated by a distance of 1 meter. So now I'm going to zoom in to the main unit so we can see how I've set it up. So here on the left hand side I've got the main control unit of the speed of sound system, and on the right hand side I've got the millisecond timer. You can see that with patch cords I've gone from the red socket to red socket, black to black and green to green, and I've also turned the speed of sound unit on using that toggle switch. And the millisecond timer is set to mode 2, so gate 1 start, gate 2 stop. I've applied power in the back of the millisecond timer, and I've also plugged that big long cable that comes with the set into the back of the control unit of speed of sound, and that takes you down to the slave unit, which is placed at the 1 meter mark. So I've zoomed back out and let's take a walk. So here is the slave unit at 1 meter, and then I've marked the floor in meter graduations all the way up to 5 meters. So I'm going to get the slave unit, put it at each of the meter marks, get a time reading for each point, and then I'm going to use that data to plot a graph and calculate the speed of sound. Let's do it. On the floor of the physics lab, and we're ready. Right, so the display of the timer unit is just reading a bunch of zeros, so this means it's ready to be triggered. So oops, so now I've just set it off by accident, so I'm just going to hit reset, and again. So all I need to do now is just make a nice loud sound in front of the control unit, and that's going to give me my first data point. So now the millisecond timer is reading 3 milliseconds, so that is going to be the value that I use for the 1 meter mark. So now all I need to do is press reset, move the slave unit to the different distances and collect more readings. Here we go. So here is the data set that I've recorded for speed of sound. In column A, we have got the distances 1 to 5 meters, and in column B, we have got the readout from the millisecond timer in seconds. So let's quickly head to the whiteboard to find out what it is that we need to plot. So we know that speed equals distance over time. Now we're going to get distance and time from our measurements, so we want these to be a function of each other, so that then we can work out that from the graph. That's the unknown. So if we swap these two around, we're going to get time equals distance over speed. And then if we separate this out, we will get time equals 1 over speed times by distance. So we can compare this to the linear line equation, so we can see that we want time on the y-axis, and then our gradient is going to be 1 over speed, and our x-axis is going to be distance. So now we know that our gradient m is 1 over speed. We can then rearrange that to find that we can calculate speed by doing 1 over the gradient. Okay, so time on the y-axis against distance on the x. X. I want to come to Insert, and then Chart, and then Scatter. And then if I make my graph look nice, I can delete that bit, change this to distance in meters, change the y-axis title to time in seconds, oops, call it speed of sound, and then I can highlight my data, right click, go to add trend line. I want it to be linear. I want to display the equation on the chart and tell me how good the fit is, please. So there we go. So what this is telling us is y equals mx plus c, and m is 0.0028. So I'm going to do a cell here. M gradient is 0.0028. And we know from the maths that we did before that the speed of sound is going to be 1 over that. So I'm going to put speed equals 1 divided by that. And that gives us 357 meters per second. So how does that compare to the real value? So Google tells me that the speed of sound in air is 343 meters per second. So it's not too far off what we got. Let's calculate percent error by doing the difference between the measured value and the actual and dividing that by the actual. And then we want to do all of that times by 100. So you can see there that we are easily within 5% error of the actual value, which is pretty good. So there you have it, a speed of sound experiment with no need to use an oscilloscope. Thanks for watching.